Well, I think we can slowly start. We have a huge number of participants today, so 250 participants so far. So thank you very much to all of you for joining. Before we start with today's speaker, Jens Nørskov, I would like to remind you that there will be other Marvel Distinguished Lecture on April 27 with Christine Persson from UC Berkeley, and also May 18, George Quest from University of Vienna. But today I am really honored to be able to introduce Jens Nørskov, who is with no doubt one of the most influential scientists in the field of computational catalysis, and whose work really led to many new ideas which had an impact not only in basic and fundamental science, but also in more applied topic of societal importance, and where his impact was also very clear in both academia and industry. So just to remind you a little bit his bio, Jens Nørskov had a PhD in theoretical physics in 1979 in Denmark. In the University of Harris. He then had several postdocs in industry, including one at IBM New York. He started his academic career at DTU in 1997, and he moved to Stanford as a chair professor and also as a director of SunCat, which is a program a little bit similar to Marvel, in 2010, before returning to DTU in 2018, also with a chair position there. He's currently the chair of the Danish National Research Foundation. He had really multiple awards, and I'm going to really pick a bit randomly because there are really a lot here, but I want to mention the Niels Bohr International Gold Medal that he received in 2018 by the Queen Margaret, the Queen of Denmark. Our sister institution, ETH Zurich, also gave him in 2017 the ETH Zurich Chemical Engineering Medal. He also received the European Inventor Award and is a member of many different academies. His philosophy, I would say, is really to simplify chemistry. I didn't say oversimplify, I really say simplify chemistry by proposing and using very simple descriptor. He had a huge impact with over 150,000 citations. So if I have to pick some of the landmark example of his work, I would probably choose the D-band model from the mid-90s that had a huge impact on how the heterogeneous and electrocatalysis community views reaction over transition metal. I will also cite probably his work on the universality of scaling relation for the oxygen evolution reaction. He also has very cited work on the performance of DFT and on revised PBE functional for computing accurately chemisorption for many different type of material on surfaces. And of course, the work is going to present today related to finding sustainable alternative to the well-known Haber-Bosch process is also one of the very interesting work and impact that he had. So it's time to let the stage to the speakers. So Professor Nørskov, please go ahead.
Thank you very much for this kind introduction. Thanks to everybody for spending a few minutes here. I'm going to talk a little bit about how the chemistry that is associated with making fuels and chemicals without being based on fossil resources. And the background is really, this was quick, doesn't work. Okay, let's hope this works now. The background is really a fantastic development that is based on ingenious chemistry, really, that has defined the 20th century in a sense. To a large extent, that has been defined by being able to take fossil resources and transform them into a lot of the products that define modern life. Of course, transportation fuels is one of them, but it also includes fertilizer for agriculture, and it includes a large number of the materials that we take for granted, all the way to pharmaceuticals. All of this is based on being able to take these hydrocarbons, mainly very dull molecules, and adding a lot of functionality to them so that they can do a number of things. And the problem is, as we all know, that this cannot continue because all of these processes, including the end use, emits CO2. So we need to find other ways of providing the same products, the same materials, the same fuels, but based on energy input from the sun, mainly, and then simple molecules like water, CO2, nitrogen, and then transforming those into these materials. And this is something we can do to a certain extent today, but it's really something where I think a lot of the chemistry and the catalysts that are needed to be able to do this still need to be invented. We know the principle. It's an electrolyzer like shown here. On one electrode, we split water, evolve oxygen. The protons go through the electrolyte, and they're used on the other electrode to make the fuels that we want. The simplest is, of course, for the protons to recombine with the electrons that have been pulled through here by the aid of, say, a wind turbine or a photovoltaic cell to make hydrogen. That's a very good starting point. But it would, of course, be much nicer if we could make a fuel, some hydrocarbon or oxygenate directly by, say, reducing CO2 in a device like this. Or if we want to make ammonia, which is the basis for fertilizers, but it's actually also a very good energy storage molecule, then we would need to be able to reduce N2. And all of this is something in principle we can do, but in practice, all of these processes that I'm talking about, or most of them, not all, but most of them are not terribly efficient today. So if you look at the water splitting here to form oxygen, it has a very large overpotential, which means that we need to put in a lot of extra energy to make this happen. If you look at CO2 reduction, it can be done, and it has an even larger overpotential. And when it comes to N2 reduction, up until recently, there was really nothing that worked. So we have a long way to go. We can do it, but we have a long way to go. What we can do today is a combination where we make hydrogen in an ordinary electrolysis cell, and then we take that hydrogen and combine it with, say, CO2 or nitrogen in a traditional thermal reactor to form the product we want. This is something we can do today. Here we're mainly up against the problem that the water splitting is still very inefficient. For the thermal processes, we do have technology that works. They are usually very high pressure and very high temperature processes, and it would be very nice if we could find alternatives that did not require such extreme conditions, because the extreme conditions are best suited if you have very large facilities. But if you make the hydrogen by a small electrolysis setup, then it would be very much more advantageous if you could have smaller production that could be decentralized. You could use the energy where it's produced in the wind turbine or in the solar cell. So there are still challenges here. Now, these challenges is really what I'll be talking about, and there's been a lot of experimentation here trying to find, say, good water splitting catalyst and many other catalysts here. And what I'm suggesting is that perhaps if we understand better what is going on during the catalysis, then we might be able to accelerate the discovery. Now, understanding means having a theory. And let me just say a few words about what I mean by theory here. Of course, the basis for everything is experiment in natural science. And there's always been theories that have been trying to systematize or understand experiments. What has happened in the last couple of decades is that computational methods, quantum chemical methods, have reached a speed and a useful accuracy so that they can actually help here. And of course, the computational work is also theoretical, but that's not really what I'm talking about. I'll be, in the following, I'll be using the computational work, and a lot of what I'll be talking about is based on computational work. I'll use it sort of as a computer experiment to teach us some of the concepts that also allow us to understand experiment and make predictions that can be tested experimentally. So that's what I'll be talking about here. The calculational work that I'll be using, I don't want to get into the details here, but it's all based on density functional theory at different levels of accuracy. I just want to point out, as shown up here, that the accuracy of what we can do with sort of semi-local functionals today is at the level of 10, 20 kilojoules per mole, 0.1, 0.2 eV, when it comes to bond energies at surfaces. And this we have established. You can see here different levels of approximation. I'll always be using the ones over here to the right that have a reasonable accuracy. The accuracy you can actually estimate by comparing to experiment. There are no sort of gold standard calculations for surface chemistry that we can use, so we have to rely on experiment. And we've been working a lot with, in particular, Charlie Campbell here, to collect high accuracy experimental data that we can use as benchmarks. And this is what I'm showing here. The fact that we have some benchmarks means that we can actually, in at least one of these functionals, we can also estimate the uncertainty of what we do. And I'll get back to that. Now, these are bond energies or adsorption energies. When it comes to activation barriers for surface reactions, we also do pretty well. This is a comparison of theory versus experiment for the few surface reactions where we've been able to find very reliable experimental data. And you can see that, these functionals do pretty well. I've included some uncertainty here, and there are uncertainties both in the experiments and the theory, in particular in the theory, of course. But we are having an accuracy which is useful, as I'll try and say. This is not This is not to say that we can't use higher accuracy. We definitely can, but we have at least something to work with at the moment. When it comes to theories or ways of understanding catalysis, then for the last 100 years, a lot of the thinking has been related to what is known as the Sabatier principle. What he introduced is the thinking that the optimum catalyst is one that binds the reactants and products not too weakly, because then you can't get it onto the surface, and not too strongly, because then you can't get rid of it. So there's a Sabatier optimum somehow. There's sort of a volcano type relationship, and you have an optimum here. And this has been very, very influential, still is. Of course, you can ask the question, which bond strength should you have on the x-axis here? That's not totally clear. And if we want to use this to discover new catalysts, then we also need to know where the optimum is. And that's not given either. So somehow we need to get shall we say, a quantifiable version of this, where you can make predictions that can be tested experimentally, so that it's a real theory where you can falsify things, and that we can use for catalyst design. And that's what I'll be introducing here a little bit. But just to illustrate how difficult it is to figure out what's on the x-axis here, let's look at a reaction which is very relevant for what I'm talking about here. What if we take CO2 or CO, and we want to add hydrogen, hydrogenate it to form just a few products here: methanol, acetaldehyde, methane, and ethanol. That's some of the base molecules that we would like to get. This is the full reaction network. All the ways in which you can combine CO2, CO, and hydrogen to form these 5 molecules. And of course, these are just the C1s and the C2s. Then you can go to the C3 molecules and so on. So it can become much, much more complicated. And all I want to illustrate here is that it is not obvious which bond strength we should be using here. In fact, it's not really obvious how one can understand what is going on here, because it is so complex that it's almost well, it's a little daunting. So and let me try and illustrate how we go about rationalizing some of this. And I'll start with a much simpler reaction, namely hydrogenation of nitrogen, the nitrogen molecule, to form ammonia. The nice thing about that is there's only one product and 2 reactants. So it's a very, very simple reaction. This is the calculated free energy diagram for the reaction over a ruthenium surface with some potassium on. And even for this reaction, you can see there are a number of activation energies and a number of energies of different intermediates that you really need to know in order to be able to optimize a system like this. The nice thing is that many of these are not really independent of each other. What I'm showing here is a plot of calculated adsorption energies of NH, for instance, here in the upper left corner, as a function of the nitrogen adsorption energy. These are calculations by Brian Raw and Mike Statt, or NH2 versus the N-binding energy. In the lower part are the transition state energies for various of the reactions, the NN bond breaking, the NH bond breaking, bond making, sorry, the NH2 bond making, and so on. And in every case, it's plotted as a function of the nitrogen adsorption energy to the surface. Of course, something like an activation energy, depending on a reaction energy, is well known in chemistry, has been for many, many years. What you're seeing here is that this can be generalized, not just for transition state energies or activation energies, but actually also for energies of intermediates. And what it means is that if we know the nitrogen adsorption energy on a given catalyst, I should say each point here is one catalyst. If we know it for a given catalyst, then we can estimate with a fairly good accuracy already all energies of all intermediates and on all the transition states in the problem. And that, of course, means that in this case, it's obvious what to put on the x-axis. It's just the nitrogen adsorption energy. And if we take experimental data, that's what is shown in the upper panel here, rates measured on similar catalysts, on similar supports, but with different catalytic materials. And we plot them as a function of our calculated nitrogen adsorption energy to these surfaces. Then you see that it really does order in a very nice way. And below, you can see what comes out of a calculation, a kinetic model, where we input all of these scaling relations, and it looks pretty much the same. So what we have now is actually, first of all, that the scaling relations tell us what to put on the x-axis. And secondly, we know the relationship between the descriptor here and the rate, and we know where the optimum is. And that's really a very big advantage. Now, this was simple. Let's go back to the reaction of hydrogen with carbon monoxide, which is what I showed you earlier. Well, before then, let me just make one point here, by the way. You can really ask the question, do we really have the accuracy to know where the optimum is? I mean, perhaps we were just lucky here that ruthenium is the best, and we do get that out. But there are actually good reasons why, even with the limited accuracy we have, that we are doing so well. And the reason is that these scaling relations are actually extremely well determined, much better determined than any of the individual points. The point is, as illustrated here, this is the scaling relation between the transition state energy for N2 dissociation and the nitrogen bond energy to the surface. What you see is that these are uncertainties, 1 sigma uncertainties for the combined calculation of those two. And what you see is that if you make an error in the calculation of the N bond energy, then you make a very similar error in a calculation of the transition state energy. And that means that the uncertainty on the determination of the scaling relation, which is really what determines where the optimum is here, becomes much smaller than the uncertainty on the individual calculations. Now, what about if we want to hydrogenate carbon monoxide? Now, as I mentioned earlier, there are many more reactions. But what we can do here, and these are our calculations in particular by A.J. Medford, when he was my student at Stanford. These are now calculations of adsorption energies of all the intermediates and transition state energies for all the possible reactions, plotted as a function of some linear combination of the carbon and the oxygen bond energy to the surface. So again, each dot here is one catalyst. And you can see that in every case, you have a very good correlation between bond energies of intermediates and then some linear combination of the carbon and the oxygen bond energy to the surface. Now, why a linear combination? Well, the point is that any of these molecules and transition states will bind to the surface with either the carbon or the oxygen end or both. And therefore, it'll always be some linear combination of those two. So these are not Brønsted-Evans-Polanyi relationships like in ordinary chemistry. These are really just correlations between bond energies of various kinds of intermediates and transition states. But it becomes very powerful because now, when you know the oxygen and the carbon bond energy to your favorite catalyst, you can also estimate all the barriers and all the energies of intermediates, and you can actually make a prediction about the rate. So why don't we do that? And it looks something like this. So let's look here at this upper left corner first. This is a heat map, so it's calculated rate, inputting these scaling relations that I showed you for making methane from carbon monoxide and hydrogen. This is at industrial conditions. The rate is plotted as a function of the oxygen bond energy and the carbon bond energy to the surface. And then, of course, we can put the values of those two for surfaces of elemental metals on here. And what you see is that the optimum for making methane is in this region here of the oxygen and carbon bond energies. Closest to the optimum is ruthenium, then comes rhodium, nickel. That's actually exactly what is known. The industrial catalyst for this reaction is based on nickel, not because it's the best, but because it's much cheaper than ruthenium, and that's why it's being used. But you can see here that even with the accuracy, and I put an uncertainty on here, even with the accuracy we have, we can actually say something meaningful about what is a good catalyst and what is not so good a catalyst. For making methanol, the optimum is at much weaker bonding, in particular for the carbon bond energy. Now, copper gets close to the optimum. It's actually the closest. These also close, but they won't make methanol. You can see over here, they have much higher rates for making methane, and therefore they are terrible methanol catalysts. In fact, copper is the only show in town, and sure enough, the industrial catalyst for making methanol is based on copper. If we wanted to make ethanol, that would be very desirable because ethanol is directly a substitute fuel even in a gasoline car. Then the optimum is sort of in between. And the problem is that there's nothing good. I mean, these look good, but again, they make hydrocarbons. In fact, what we can do when we have these three products, we can ask the question, which is the main product as a function of these two parameters, descriptors, that's shown here. The green area is where you make primarily methanol. Blue is where you make primarily methane. And this red sliver here, that's where you would make ethanol. And there are no elemental metal even close. And that's exactly what is known. There is no industrial process for making ethanol directly by hydrogenating CO today. There are, what we can do, of course, is we can begin to look at intermetallic compounds. And each cross here is one intermetallic compound where we can calculate those two parameters and put it in here. And if you look at the zoom in here, there are actually some materials, cobalt, platinum, copper, cobalt, that make some ethanol. And that's also known experimentally, but they're not really good. You can see they're sort of not deep red with a selectivity of 1. They're sort of a mediocre selectivity, and it's still not good enough to make an industrial process. Another example is, and getting back now to the water splitting, the electrochemical water splitting. If you want to split water in an electrochemical process, what you do is you extract protons and pull out the electrons. You start with water, then you form OH, then you form O, and then you add another water molecule, extract a proton and an electron, form OH, and so on. And it turns out in our analysis that it is actually the formation of OH, the formation of the OO bond. That is the most difficult step here. And again, we have scaling relations relating stabilities of intermediates and activation barriers to stability of intermediates. And that directly allows us to, again, make these volcano relationships. We have a descriptor which is related to the way the surface bonds to oxygen, and we have an optimum here. The blue is when we make a full kinetic model. The red is if we just look at the thermal chemistry. I mean, there are important differences, but when it comes to sort of where is a good catalyst, even the simple thermodynamic analysis gives a pretty good picture. Now, the fact that we can make these volcano-shaped relationships gives us a tool for trying to help designing catalysts. And the first example actually was one that where Klaus Jacobsen here at the Topsø laboratories, he said, well, if it looks like this, and this is what we gave them, then if you have molybdenum here that binds too strongly and you have cobalt over here that binds too weakly, then if you can make a material that has both cobalt and molybdenum at the surface, you ought to be in the middle here. And we did the calculations, that's exactly where it is. But the experimentalists at the Topsø laboratory also did the synthesis of a material which is cobalt-3, molybdenum-3 nitride. It's a metal, mostly just cobalt and molybdenum at the surface. And what you see here are now experimental data, rates. This is turnover frequency, that's rate per site. For making ammonia as a function of the amount of ammonia out. You have iron down here. You have ruthenium, much higher rate. That's exactly what you see over here. Ruthenium has a higher rate than iron. And then you have this cobalt molybdenum intermetallic subnitride here doing pretty well, basically as well as ruthenium. And that came out of this very, very simple analysis here. Of course, this is only simple if you found the right descriptor so that you know where you want to be. Another example is electrochemical. This is related to the making hydrogen, the recombination of protons and electrons to form H2. Here, it's pretty obvious that the descriptor is the hydrogen adsorption energy to the surface of the catalyst. And it turns out that if you take experimental data, these are data from many, many different laboratories, and you can find the references in this paper here, and you plot them as a function of the calculated free energy of hydrogen adsorption, then again, you get a very nice volcano, and you will observe here what everybody knows, that there are very, very good catalysts for this process, but they're also very, very expensive. They're all in the platinum group materials. So once we know that all we need to find is a material where the surface binds hydrogen with a free energy, not energy, but free energy of adsorption around 0, then what we could do is we could look through all of our calculations that we've done for many years and see if there was something interesting there. And what we found was that molybdenum disulfide, a layered compound, and not the basal plane of molybdenum disulfide, but the edges of molybdenum disulfide particles actually should bind hydrogen very close to delta G equals to 0 and should be a reasonable catalyst, not perfect, but reasonable. And that actually turned out to be the case. That was shown experimentally first in the group of the Korkendorf and since then by hundreds of authors. And the point is that it is in fact the edges of these nanoparticles of MOS2 that does the catalysis as suggested by the theory. And now the game becomes how many of these edge sites can you pack into your catalyst. So what people have been doing is they've been optimizing this nanostructuring materials to get more and more of these active sites. And what you see over here is a summary of data from the literature and lots of references down there. This is the overpotential, that is the potential needed to get a current density of 10 milliamps per square centimeter of hydrogen evolution. And for platinum, it's 0. So we'll never get as good as platinum. And if you go back 10, 15 years, then typical materials would have fairly large O potentials. And now that has really gone down enormously. Since then, we also got phosphides and sulfur phosphides. And now we can actually split water, make hydrogen, which is part of the electrolysis process, make hydrogen with a fairly low O potential, not because it's as good as platinum at all, but simply because we can pack many active sites into the catalyst. And this has really been a tremendous development here. Of course, what we really would like to do is to find something better for the water splitting part. I mentioned already that we have a fairly large O potential. Let me just show this theoretically here. I'll get back to experiments in a moment. But the point is, we should be able to split water at this potential here, 1.23 volts. Typically, if we want reasonable current densities, we have to pay 0.3, 0.4 volts extra potential in order to get a current density in that order of magnitude. Still, we can try and optimize here, and here's the optimum roughly for reasonable current densities. Here's a 2D plot where we have one more descriptor, the OH bond energy. For most of the reasonable materials, that one doesn't matter. That's why we can show it in 2 dimensions there. But in this range here, it's just a matter of optimizing this parameter here to be in the range just around 1.5 volts. Now, it would be nice if we could find something else here. And we have really been looking, and let me just say immediately, without much success. This is a terribly complicated problem. Now, you would think that since you are running at very oxidizing conditions, then transition metal oxides should be good. So we made a big search here, trying to find criteria for better catalysts. And here's a big screening study that Shenbin Wang did here. He started with about close to 50,000 different oxides in the materials project. And he just asked the question, are they stable? Just the bulk oxides, are they stable under reaction conditions? And after going through some not very rigid criteria, these 47 or 48,000 materials, only about 68 would be stable under these conditions. And these are actually those that are stable both for the oxygen reduction reaction or the oxygen evolution reaction. And then Kasum, and I don't know why he's called 68 here, he took those that are stable under the oxygen evolution reaction conditions together with Shenbin here, and then studied the many different surfaces to see if any of these materials would be kind enough to have descriptor values in the right range. And the point is very few are in here. Out of these 47,814, the stars here, that's iridium oxide. We knew that already. And then there are a few other materials, mostly antimonates, and that was actually known from the group of Nate Lewis already in 2017. So it's been really disappointing. And as you can see, the main problem we have is actually not just to have a high catalytic activity. It's actually also that most of the materials won't be stable under the conditions of the reaction. So stability is a terribly important parameter here. We had a little more success looking also at water splitting, but just water splitting, not to form oxygen, but to form hydrogen peroxide. It turns out that you have one volcano for making O2 and another one for making hydrogen peroxide. It's the same scaling relations. And the point is here, this is much less studied. Some of the best catalysts known here are something like bismuth vanadate, but it turns out zinc oxide, for instance, and certain facets of zinc oxide should be extremely good according to the calculation. And here are these are calculations by Sarah Kelly, and in the group of Xiaolin Cheng at Stanford, they synthesized these and measured the rate for making hydrogen peroxide, and you can see this is really how it came out. So again, where you can help guide design by understanding well enough what are the descriptors and where's the optimum. But this is not all. Here is a plot sorry, of the transition state energy for nitrogen dissociation and the nitrogen bond energy. You've seen it many times. Here's the scaling relation. But imagine you could vary those two parameters independent of each other. Now, clearly for the transition metals, you can't. But if you could, then you can get a much, much better catalyst. Estimates that I've heard from my experimental friends is that hundreds of thousands of materials have been tested as catalysts for this reaction, or at least tens of thousands. And what you were, and not much better has been found. Well, you saw the cobalt molybdenum here, but my guess is that most of these materials have really been just running up and down this scaling line here. We really need to find completely new types of catalysts that could get us down into this region here. And this is true of other reactions as well. This is now here's the scaling relation between the transition state for forming the OO bond in the oxygen evolution reaction, plotted as a function of the usual descriptor of this process, the bond energy of oxygen minus that of OH. And you see materials up here, you see the optimum is down here. So again, when we optimize here, we're sort of running way off the real optimum. So you can say these scaling relations are, of course, what made it possible for us to rationalize a lot of the observations that have been made. But it really turns out also to be what makes it so difficult to find something radically different. And here, if you look at this oxygen evolution catalysis, then you really don't get much better here by optimizing along this line. And this, I think you can probably see if you look at the literature over the last 10 years or so. These are measured O potentials at a certain current density, both in alkaline and acid solution. And what you see is that in spite of a large number of experimental studies, and this is just a subset, but a representative subset, then not much has happened in terms of the O potential. And that, again, I think is an indication that we are optimizing along this line, but we're never getting into the really interesting region here. So we need somehow to be able to find catalysts that have a functionality beyond a planar surface that can bind all the intermediates and all the transition states by exactly the same in exactly the same way. There are, at least on the computer, you can find such examples. This is getting back to the ammonia synthesis, the thermal synthesis. And what you see here is that if you have dimers of one material embedded in an inert material, you can actually get into the interesting region. These are calculations by Ayu Singh and Brian Raw and Joey Montoya. And the point is, unfortunately, that at least at the reaction conditions of ammonia synthesis, such dimers won't be stable. They will segregate out, and so we need to find new ways of synthesizing materials that are, shall we say, nanostructured much better than what we can usually do. My last example is related to the need to find catalysts for electrochemical reduction of N2. And here is a plot of the usual kind that you've seen now many times of some measure of rate. It's a limiting potential here. As a function of two parameters that are obviously correlated, related to the stability of various intermediates in N2 reduction. You see the optimum is down here, and everything is really way off the optimum. So it looks as if finding a really good catalyst here might be difficult, but there's an even worse problem, because if we now look at rate or some measure of rate as a function of this line here, just forgetting about coming down here, just as a function of this scaling line, then it looks something like this. You have an optimum there around rhenium, ruthenium. That's what you see down here. But then we can plot the rate of hydrogen evolution on the same scale. And you see that rate, this is the log scale. So that rate is orders of magnitude larger. So we have the problem that if you want to reduce nitrogen by adsorbing nitrogen and adding protons and electrons, then you can also just adsorb the proton and electron and add another hydrogen to that and form H2, and that dominates completely. So the selectivity is poor. And you can think a little bit about that. And obviously, what you need to do is to make sure that you can get nitrogen onto the surface before the proton or the electron comes. And there are various ways you can do that. Here's the mathematics for optimizing this. But basically, what you need to do is to either limit the access to protons or the access to electrons. And you can do that in various ways. For instance, you could imagine that you did not have an aqueous solvent, but a non-aqueous solvent, or you can have a hydrophobic layer on top of your catalyst, or you can limit the access to electrons for that matter. And those we are suggesting should be good ways of getting a reasonable selectivity. Now, this is a field that making ammonia from electrochemical reduction of N2 that's really exploded in the last few years. And here's a summary of some of the data. What is shown on this axis is the so-called Faraday efficiency, that is the selectivity. So 100%, 10 to the second, that's where we want to be. And this is the rate. And you can see there are materials all over the place, but not all the data are equally reliable, because some of the data people have not made blank tests or have made blank tests but not checked with isotope labeling that the ammonia you make actually comes from reducing the N2. And so if you only look at the red data points, they are the best ones, then some of them are open and some of them are closed. the closed one are the ones where you have a non-aqueous solvent, and you can see they really dominate for the high Faraday efficiency data. In fact, there's only one set of data where there's actually a quantitative isotope test. So that's the most reliable data. And it's based on an interesting process where lithium is the intermediate here. And it actually goes back to experiments done in the 30s. And then it was rediscovered in the 90s. And now it's being rediscovered. And now we can actually see now, these are data now from the group of Korkendorf showing that quantitatively all of the ammonia that is made comes from reducing the N2. And here's the process illustrated down here as we see it. You deposit lithium. Lithium is very reactive. It dissociates nitrogen. And then you add protons and electrons from the electrode to this, and you form ammonia. And this actually can work. And here's a typical experiment. This is the blue. Here is the potential of the working electrode as a function of time at a fixed current density. And it sort of looks quite all right. And then after about an hour, things go terribly wrong. And so you can get efficiencies of about 20%, but the problem is it's unstable. And of course, one reason it's unstable is that you keep depositing lithium and eventually you run out of lithium. So we actually found a more clever way of doing this by simply cycling the potential. And now you can get to Faraday efficiencies of the order 37% and run for hours and hours and hours. So we're beginning to be able to make ammonia electrochemically, but we're only just beginning. And I think this is an area that will take a lot of development before we're really there. So let me try and summarize what I've been trying to say. I've been trying to convince you that there are some concepts, these scaling relations, that really provide a very simple way of understanding trends in catalysis, both heterogeneous catalysis and electrocatalysis. And I might add, and this is pioneered here by the chair of this seminar, in homogeneous catalysis. It does provide design criteria, but we really need, on top of being able to optimize to get to the top here, we also need to find completely new catalysts that have different kinds of active sites than what we're used to, as I've tried to illustrate. And what we really need are non-traditional solutions. I've been trying to illustrate that by changing the reaction conditions, things can be very, very different. There's no doubt that we need inspiration from homogeneous catalysis and enzyme catalysis. And this is just to illustrate that scaling relations hold also in homogeneous catalysis very well. But of course, there are many, many challenges ahead, lots of work for ingenious scientists here. And I think, to me at least, the really important one is to find oxygen evolution catalysts that have much low O potentials, because that will make water splitting much, much more efficient, and that will really lead the way to a sustainable future. Let me make sure that I mention all those students, postdocs, and collaborators that have been contributing to what I've been talking about. Chen-Bin Wang, Kasun Gunasoya, Vanessa Bukas, Ankit Jain, Mega Anand, and Hao Li, postdocs at DTU since I moved there, and the Stanford students that I've been finishing lately are Yu Singh, Brian Raw, Mike Statt, and Sarah Kelly, and then a number of former collaborators and students who have made great careers elsewhere that you can see here. A lot of them have contributed a lot here. And then a number of collaborators, both in experiment and theory, and I think in particular the experimentalist I would like to stress here, because without a close collaboration with experiment, a lot of this would have been fairly uninteresting. And in particular, Ib Korkendorf and Jakob Kipskorp at the DTU, Tom Jaramillo, Matteo Cagnello, and Xiaolin Cheng at Stanford. A number of collaborators at the Topsø laboratories, Claus Christensen, Bjørn Clausen, Paul Georg Moses, Søren Dahl, Beat Hinnemann, and collaborators on the benchmarking, Charlie Campbell, Gert-Jan Kroos at Leiden, and Alan Lantz at SLAC. And finally, let me make sure to mention who is funding all of this. The early work, US Department of Energy, both through the SunCat Center and through the Joint Center for Artificial Photosynthesis, and lately, in particular, the Willum Foundation, the Willux Foundation's been a very generous funding to this. And thank you very much for your attention.
Well, thank you very much for this very inspiring lecture. The stage is now open for question. You have two ways to ask your question. Just raise your hand and I will see it, and I will basically, I think I will allow you to talk. Or you can also use the Q&A chat if you feel more comfortable with that. But I think raising your hand will be the best option. So in the meantime, when you get familiar with the system, I will ask my first question that is very much related with the paradigm for paradigm shift for new catalyst, and also the inspiration from enzyme catalysis and homogeneous catalysis. What people do in homogeneous catalysis, right? They had two functional groups that will perform the different tasks, and although there are examples in the field of electrocatalysis, it's not exploding this way of trying to come up with like composite material or two different catalysts that are close to each other, two different materials that are close to each other that could eventually perform one task and the other. So why do you think that it's actually not booming this way?
I think, first of all, I think there are two issues. First of all, having just sequential catalysis with different functionalities, that will only solve some problems. I mean, that wouldn't work for ammonia synthesis, for instance, or something where you are basically performing the same task over and over again. What one needs to a large extent is to have more functionality in a single active site. And that certainly you do see in enzymes, you do see it also in some homogeneous catalysts, namely where you have, for instance, a primary bonding site, but then you have perhaps a ligand that comes out and can do hydrogen bond to a transition state, but not to some of the other states. And therefore you can change the relative bonding of various states, and changing the relative bonding of various states, that's exactly getting off this scaling line. So if, for instance, getting back to ammonia synthesis, if you can find a way of stabilizing the transition state for N2 dissociation and not stabilize atomic nitrogen on the surface, then you're in business. And there are ways of doing that, because that's what you do when you adsorb an alkali metal on your surface, which is what is being done in this process. But this is just an example. You can, I'm sure we can find ways to do similar things for other reactions. The problem is keeping it stable.
Yeah.
And that I think is the main challenge here.
I think Michael would like to follow up. Michael Gretzel.
Yeah, hi Jens. Can you hear me?
Very well, I think.
Okay.
Hi, Michael.
Jens,
Oh, yeah, I hear you well. Thanks.
Jens, I just wanted to ask you about the oxygen evolution catalysis. We all know that the manganese complex that nature uses, this cubic manganese complex, has almost ideal spacing of the energy levels. And so you said, you know, a lot of people have tried and they never got to the better result. Why don't we use it as a model to inspire ourselves how to get a good catalyst?
Yeah, I mean, yeah, and a lot of people have tested various manganese oxides. I can promise you, and they are quite good actually. I'm not 100% sure that even photosystem 2 is completely ideal, but it's certainly good enough for photosynthesis.
Yeah, and it's much better. Please go ahead.
Well, I think we need something even better than that, because we need it also to be stable for years, or at least months. And we need it to be able to run at much higher current densities. And you know, we have more requirements. But yes, it is a place to be inspired. And it turns out manganese oxides are quite good. They're not very stable, but they're quite good.
Okay, thank you, Jens.
Hello. Thanks a lot for the talk. This is Sasha from Schrödinger. I have a question about the solvents. If you think it's important for the simulations, and if you try to use any solvent models with your DFT. Thanks.
Yeah, I mean, we have tried that, and we do that. It's not simple at all. What we've mostly been using is water, and trying to describe that by an explicit water model and then some implicit solvation. But this is one of the weaker points in everything we do at this point.
So do you think the effects are big or small, like on your results?
I mean, I think in the cases where they are significant, and we do include them at a certain level of approximation, but we can certainly do better there. I think we have at least a qualitative understanding of how it affects things, but we can do better, without a doubt.
Thank you.
Axel Gross.
Yeah, can you hear me?
Yes.
Oh, yes.
Thanks again for this nice talk. Like always, I have a kind of general question. You mentioned these concepts for reactivity, but you also mentioned selectivity at some points. And my question is, do you think the same understanding of selectivity as we have of reactivity, and whether we also might need a better understanding of selectivity in order to make progress?
I mean, we definitely need both. I did speak quite a bit about selectivity, but I'll just highlight what I think is the big challenge here. And you can see it in this slide. If you look at the reactivity volcanoes, if you like, then things are varying smoothly. If you're around the optimum, then you see the width of a contour is several tenths of an EV. Okay, and that means that with the accuracy we have today, we can definitely say whether we are sort of close to the optimum in terms of rate. Now, if you go to the lower right corner, which is the selectivity plot, there you can see that the variation from blue to green is happening very fast. And there we definitely don't, if you're close to the border, then we don't have the accuracy to say whether you are on one side or the other. So selectivity is very important. In some cases, we do have the accuracy, but if you're very, very close to the border, then we need a higher accuracy than we have today. Does that answer your question?
Yeah, in principle, I still wonder, you didn't talk how you determined this selectivity. So is there easy concepts to understand selectivities, or is it a complicated issue?
Well, I mean, it is. I mean, this plot is just a linear combination of the three other plots. There's nothing else to it. I mean, it is just the rate of methanol divided by the rate of methanol plus the rate of methane plus the rate of ethanol.
Okay.
And then color coded.
Okay.
So in a sense, it is all in there. We don't, and the same descriptors hold. I mean, that, as you can see here, this completely explains why copper makes methanol only, and rhodium and nickel and cobalt only make hydrocarbons. What have you? I mean, there's no doubt that we understand all of these things, but it does require, if you're close to the boundary, it does require a higher accuracy.
Okay.
Simply because it's given by the difference between two activation energies and not just an activation energy varying.
Okay, yeah, thanks a lot.
Yeah.
Okay, Mr. Hermida, next.
Hi, good afternoon, Jesus. First of all, really nice talk. Thanks really so much. I had a question regarding the lithium-mediated nitrogen reduction. Mostly, I would like to know your thoughts about using other catalysts rather than lithium, but still making a solid electrolyte interface. So, like to try to move away from the lithium plating for the very negative potentials that it requires.
Yeah, well, it is so far the only system where we have a sort of, that I know of, I should say, where we have a reliable large amounts of ammonia synthesis electrochemically. It is a nice catalyst in the sense that lithium is very, very reactive to nitrogen. It even forms a nitride very, very easily. But of course, it requires -3 volts to plate, just like when you charge your battery. And that it would be very nice to find a way to prevent protons from coming too fast in without a system like this. I think that the secret, and that's what our modeling says, the secret is all in this SEI layer that forms on top of lithium when you plate lithium in a system like this. This is what controls the rate of diffusion of protons and lithium and nitrogen to the surface, making sure that you have exactly the right ratio of those rates.
So is it necessary to
able to control that in a different way? Yeah, sure.
So is it necessary to form a film of lithium so there can be a solid electrolyte interface?
Yes.
Okay.
That's what we believe.
Perfect, thanks.